Today we start eigenvalues and eigenvectors through invariant subspaces. Finally, linear maps get inspected by what they refuse to throw away. We will define invariant subspace, eigenvalue, and eigenvector. Look at pictures. Then prove eigenvectors from different eigenvalues are linearly independent. A subspace U is invariant under T if every vector in U gets mapped back into U. The zero subspace and the whole space always qualify. Null spaces and ranges also qualify. Not thrilling, but mathematics often begins with low standards. For T of xy equals 2x, 1/2 y, the x-axis is invariant. Vectors on the x-axis stay on the x-axis. The vector may stretch, but it does not escape the line. A rare example of a vector respecting boundaries. The diagonal line is not invariant for this operator. A vector can start on that line and land somewhere else, because apparently even lines have abandonment issues. The simplest non-trivial invariant subspaces are one-dimensional lines through the origin. If a non-zero vector v is sent to a scalar multiple of itself, t versus equals lambda v, then lambda is an eigenvalue and v is an eigenvector. The vector 0 is banned from defining eigenvalues, because 0 would make every lambda look special. 0 is talented at causing fake achievement. For this stretch and squeeze operator, every non-zero vector on the x-axis is an eigenvector with eigenvalue 2. Every non-zero vector on the y-axis is an eigenvector with eigenvalue 1/2. A 90-degree rotation over the real plane has no real eigenvectors. It turns every non-zero direction away from itself. Dramatic, but mathematically useful. Now the first serious theorem. Non-zero eigenvectors corresponding to distinct eigenvalues are linearly independent. Translation. Different scaling behaviors cannot secretly be redundant. Mathematics occasionally has standards, despite appearances. Suppose the eigenvectors are dependent. Choose the first vector that lies in the span of the previous ones. So versus sub k is a linear combination of the earlier vectors. Because k is the first failure, the earlier vectors are still linearly independent. Apply t to both sides. Each eigenvector versus sub j turns into lambda sub j times versus sub j. Now multiply the original equation by lambda sub k, so the left sides match. Subtract. We get a linear combination of the earlier vectors equal to 0. Since the earlier vectors are independent, all those coefficients must be 0. The lambdas are distinct, so the only way out is all a's are 0. Then versus sub k equals 0, contradicting that eigenvectors are non-zero. So the list must have been linearly independent. Invariant subspaces let us study an operator by pieces. Eigenvectors are the one-dimensional pieces where T acts by simple scalar multiplication. Next, we use eigenvectors to talk about diagonalization. That is when a matrix becomes almost embarrassingly easy, assuming it has enough eigenvectors. Which of course it may not, because why would life be convenient?